In this two-part series, we will create a neural network and backpropagation from scratch. The implementation will be GPU enabled with amazing performance. Against the standard neural network implementation from PyTorch, our implementation from scratch trains much faster. The task our neural network will perform is handwritten digit classification using the MNIST database. So, without further ado, let's begin. Alright, if you haven't already watched part 1, I highly recommend you go do that, because that is where we build the neural networks framework. Now we're going to implement backpropagation and enable the GPU. So to begin with, we will code the toDevice methods. That is the method that sends our neural network to the GPU. It takes as input device, and then it sends the weights to the device, and the same for the bias. Next, we'll do the same for the neural network class, because this is the method that will call the toDevice method on all of our layers in our neural network. Then, in the ReLU method, we also have to send the tensor that we make to the device. And now we can just call toDevice because we return self in the method. Now we just have to define what device actually is, and we are going to use torch to see if CUDA is available. And it is much easier here if you use Linux, so you can just use Windows subsystem with Linux. That is what I do. Otherwise you won't be able to use the GPU in a notebook. And now we'll just print the device to see if CUDA is available. Now we also have to send the inputs and the labels to the device, so we'll do that. We'll have to do the same down here. And now we can try to run it to see if everything still works. As you can see, we're now using the GPU and everything still works. And as you can see, there are 42,000 images in the dataset, and everything still works lightning fast. Alright, now we're ready to implement backpropagation. To begin with, we will implement the cost function. And that is the function that will take the correct labels and the predicted labels and decide how wrong the neural network currently is. So we'll get the max logits, that is the prediction of our neural network. And then we'll use cross entropy loss, because that is just a common loss function that works very well and is implemented like this. And we'll get the probability that our neural network has assigned to the correct label. And that might be a very wrong probability, or it might be a good probability, depending on how well the neural network performs. And then we'll get the loss and return both the loss and the probabilities. Alright, now we can implement backpropagation. So backpropagation is where we go from the output layer all the way down to our input layer in a reversed order. And our layer will have gradients for both our weights and our biases. And we'll start by zeroing them out so that the gradients are not affected by previous iterations. So in our layer class, we have to create these gradient variables. We'll start by also creating the variable that is the derivative of the cost function with respect to our activation value, because we have to keep track of this value when we do backpropagation. Then we'll create the gradients for our weights and for our biases. And there are as many gradients as there are weights and biases. And we'll also have to send these gradients to the device so that we can continue to use the GPU. Alright, now let's get the loss and the probabilities by running the cost function that we just implemented. We'll save the loss. We'll have to implement the functional library from pytorch, because that allows us to get the prediction for our neural network. And I should say predictions because we're calculating multiple predictions because we have multiple samples in our batch. So now we can calculate the derivative of our cost function with respect to our activation value. And because we use cross entropy laws, we can define the initial derivative of the cost function with respect to the activation value like this. Now we create the backpropagation for our output layer. And we do that by picking the last layer, which is the output layer, and call the compute gradients on it and supply it with the derivative. But we of course have to create this method, so we'll do that right now. So it's a batch of derivatives because we're working with batches. We'll save the derivative so we can keep track of it. And now we calculate the gradients for our weights, and that is the inputs, that is matrix multiplied with the derivatives. And for the bias, we take the sum of this derivative DCA, but we sum up the batches so that we get one column where each row is a summed derivative for each bias. Then we set the current DCA to the DCA we just calculated, because that allows us to continuously update our derivative of our cost function with respect to the activation value. So now we can calculate backpropagation for our hidden layers. And we'll have to go through the hidden layers in reverse order, right? So from the output to the input, except for the output because we just calculated that. we'll set the next weights, which are the weights that go from the layer we're looking at to the layer after it. And now we have to calculate the derivative of our activation function, and we use the ReLU. And so we'll just define the derivative of the ReLU activation function, and it is quite simple. If the value is greater than 0, then we return 1, otherwise 0. Next, we have to calculate the derivative of our cost function with respect to our activation value, and that is calculated in our hidden layers like this. And now we call the compute gradients on our current layer. We'll set the current derivative of our cost function with respect to their activation value so that we can use the updated derivative in the next iteration. And now we've coded backpropagation. Alright, I quickly want to clarify some things before we continue the video regarding to the math. So this DCA that we calculate, that is the DCA that comes from this multiplication, right? Because we use cross entropy laws, we're allowed to combine these two into the first DCA, right? Then we use this DCA in our compute gradients for our output layer so that we know the influence the weights and the biases have on the cost function. And so we already calculated this, right? That was from the DCA. That's the DCA where we could combine these two. So we just have to multiply with Z with respect to W. That comes out to be the output from the previous layer. So in the code, that's what we do. The output from the previous layer multiplied with DCA. So this component is here, and these two components are inside this DCA batch. Alright, but what about for the next layers? Well, it's the same thing. Now we save the DCA, and in truth I've been a bit naughty when I named these variables because it's not really the DCA value, it's a combination of calculations. Now for the remaining layers, we're working in this for loop, and we start by calculating ReLU prime, and then we calculate DCA, but this is not actually DCA. This part here is DCA. And then I multiply ReLU prime on top of it because this part right here would be ReLU prime, and this is the DCA. So this is DCA, ReLU prime, and then what are we missing? Well, we're missing Z with respect to W, and we know that that just comes out to be the value from the previous layer, AL-2, if we were working with AL-1. And that's why in the code, we once again just multiply with the output from the previous layer. And the DCA batch will now contain ReLU prime multiplied with DCA. That is what is inside this DCA batch variable. So I hope that clarified any confusions you might have had. Now we have to code the method that updates the weights and the biases. And it's quite simple. We go through every layer in our neural network, and then we call the update weights and bias method and supply it with the learning rate and the batch size. And then in the layer class, we have to define this update weights and biases method. So now we can update the weights, and we do that by multiplying the learning rate with the gradients for our weights and then divide with the batch size. And we do that because we take an average step down the hill, and that allows us to perform training much faster than taking a step down the hill for every single sample. And we also have to update the biases, of course, with the bias gradients. Now that we have a method for updating the weights, we can create the training loop. So we'll define the first variable, which is the number of epochs. So how many times do we want to loop through the training data? And we are just going to put 10. That might be too many epochs, but for the purpose of this video, it's not really important. We'll set the running loss. And now we use the train loader to load our inputs and labels. We remember to send the inputs and the labels to the device. And then we can calculate the outputs by calling model.forward and supply it with the inputs. Then we can calculate backpropagation by supplying the outputs and the labels. And finally, we update the weights and we set a learning rate, and we are just going to use 0.001. And we also supply it with the batch size so that it knows what to divide with. And then we update the running loss. Finally, we can calculate the average loss and print it out. As we can see, the model is learning, and it's learning very fast. It's utilizing the GPU to quickly calculate the matrices and update the weights. And as we can see, we get a good accuracy score. And when we look at a single batch, we see that it classifies the digits correct almost all of the time. So I hope you guys enjoyed the video and that you learned a lot. I know I did when I made this project. If you enjoyed the video, feel free to leave a like and subscribe. If you have any questions, leave a comment in the comment section, and I hope to see you in my next video.